Okay, so I'm over here. I'm going to find my O2, and I'm going to write my mass there. So we have 0.143 grams of O2. So that's what's given. And then notice that what we're going to do first is to come up with the mass of each reactant. So actually we have two parts. So I'm going to call them 1A question mark grams here for that reactant, and 1B question mark grams here for that reactant. Okay, so we're going to do that right now. And then I'm going to turn you loose, and I got calculators if you want to borrow one. Then for 10 points extra credit now, all of these extra credit points, what they're going towards are your missed assignment points. I don't know if I've ever made that clear. It's not labs and it's not homework, or it is homework. It's homework or assignment, yeah. But it's not test points. So then I'm going to turn you loose, and we're going to go here. So it says, based upon this mass of O2 produced, what mass of TiF4 will be produced? We'll call that 2A. And then 2B is question mark, what mass of Br2 will be produced? So stoichiometric there's 4 different stoichiometric calculations up there. So does your next slide look like this? Okay, great. So on a test, you'll have to knock out the molar masses of all that stuff. Yes, but we're going to refer to this. Okay, so let's go ahead and do the first one. Let's do 1A. Okay, so for 1A, we're going for the mass of O2, 0.143 grams of O2 to question mark grams of TiO2. Okay, so what's our first term going to be?
0.143 grams of O2 over 1.
Perfect. 0.143 grams O2 over 1. I love it. Okay, so now our pattern is to go from grams to moles. So if you look at the previous slide, how are we going to do that?
Molar mass of TiO2. Is that 1A?
This is 1A, but we're not going to use this the TiO2 first. We're going to use the molar mass of
O2.
O2, exactly. So the molar mass, yeah, so it's 16.00 grams per mole, and we want grams to cancel, so we're going to flip that thing. Okay, so it looks like this, 1 mole of O2 over 32.00 grams. Yep. Cool. Now this is the heart of the stoichiometric calculation, so this is what you guys handed in. And so what I would do is I would draw a line, I would write units of moles of O2, because that's what we want to cancel, and we're going to TiO2, so I would put moles of TiO2, and then I would fill in those circles.
Yeah, because whatever you're trying to find is the one on the top.
Yes, exactly. Whatever you're trying to find is on the top, and whatever you're going from is on the bottom. So let's start with the O2. What number goes here in front of the moles of O2? 3. I buy that. Is everybody good with that? Very good. Well, what number goes there for the moles of TiO2? There's also 3, but it's because of this 3. We good with that? So if we do that, then the moles of O2 cancel. We're left with moles of TiO2. And now we need to use the molar mass of TiO2, which if you look at the previous slide, we want, we want moles to cancel, so we're going to use the unflipped version of the molar mass of TiO2, which looks like this, 79.87 grams of TiO2 over 1 mole of TiO2. And I think I mentioned this before, but this is another example where sometimes students will say, you know, you got a ratio of 3 to 3. Why not reduce it to 1 to 1? And I like the 3 to 3 because then I can look up at the balanced equation and see the coefficients of 3 and 3. How many sig figs do we need to round it to? 3. I'm liking it. Oh, she's wearing her ring. I love it. How'd we do? I got 0.143 357 grams of TiO2. If you've ever I haven't bounced my checkbook in like forever. I just take the bank's word for it. So, but when I used to, it's like I would do it and I get a number and I do it again, I get a different number, and I do it again, and whatever numbers matched, I'd be like, oh, that must be it. Oh man. Okay, so that was 1A. So 1B looks like this, where we're going from, again, 0.143 grams of O2 to question mark grams of BrF3. So what's the first term going to be?
The same thing as the top.
The same thing as the top. And actually, sometimes it feels like deja vu because the second term is the same also, isn't it? Yep. We're going to take that 0.143 grams, and we're going to multiply it by the molar mass of, actually the flipped version of the molar mass of O2. 1 mole of O2 over 32.00 grams of O2. So our grams of O2 cancel, we're left with moles. Now this is that heart of the stoichiometric calculation. I'm going to go ahead and draw my line. I'm going to, like JC said, I'm going to put the thing I want to cancel on the bottom, the thing I want to get, so moles of O2 on the bottom. We're trying to get to moles of BrF3. I'm going to make my circles here. So what number goes here in the moles of O2? 3 again, yep. Okay, so what number goes there with the moles of BrF3? It is 4. Very good. So putting it that way, our moles of O2 cancel. We're left with moles of BrF3. And then we did this in the previous unit. To get from moles to grams, I used the molar mass. So on the previous slide, we're going to use the unflipped version of the molar mass. And it must look like this. 136.90 grams of BrF3 per mole of BrF3. So all the units cancel except for grams of BrF3. And then how many sig figs? 3. That looks like 3 again. Have a good weekend. So is this what y'all got? Okay, we got 0.816 grams of BrF3. So yeah, so somewhere in, in the margins or something, go ahead and work that next problem. Maybe it's even on the next slide. So go ahead and work 2A and 2B.
When we say that 2A and 2B were just the other two sides of the...
Yeah, it's the other two products. So based upon that mass of O2 produced, what is the mass of TiF4 for A, and what is the mass of Br2 for B? Very good. My computer's froze. Come on, guy. Come on. Oh my gosh.
It was like 9 o'clock. If I was in one house by like 9:40, I'd be here on time.
All right, now we're cooking. Okay. Good job. Got you all down for 10 extra credit points. Yay! So we were given the mass of the O2 right here, okay? And the first part we found the two masses of the TiO2, the two masses of the two reactants, and the second part we found the two masses of the other two products. And so the mass of the reactants should equal the mass of the products, kind of like what we did yesterday in a perfect world. And they do. Okay? Yes. So just a little bit more to talk about here. I think we've got time to a couple other subjects. But, yeah, this homework will be due, my computer's going crazy here. This homework will be due on Monday. So, yeah, we have class on Monday, so don't get like Thanksgiving fever and not come next week. Because just Monday, well, unless you have classes on Tuesday.
That's what
Yeah,
I'm saying.
Monday,
You get
Tuesday.
classes, but I just didn't.
Yeah.
Well, I don't have Tuesday class either, because she's gonna be out of town, so only one class on Tuesday.
That's awesome. You have a lab class? It'll go fast. And we have a fair bit of class like after,
Yeah, no, what the heck?
yeah, I know. So just,
That's not right.
usually we come back from Thanksgiving, it's like, oh, we're almost done. Unless we come back Thanksgiving, we're like,
We still
no,
have like a month.
we do.
I think that'll go by the fastest though. Most
Yeah.
of my classes are done with like all of their unit tests, so all we have left is the final. So we're pretty much doing like nothing.
Treading
Most
water,
of my
yeah.
classes, yeah.
Oh,
Just
yeah.
random stuff.
It's coming up.
I believe it's already Thanksgiving.
I know.
I feel like Thanksgiving should still be like a week or two. I know.
So this is kind of a quick diagram of what's due on Monday. So all the question mark grams, they gotta be filled in, right? Bottom line is, if you read A gives you 4.7 grams of aluminum, and B gives you 4.7 grams. I wish they would have picked a different number.
Yeah, what the heck?
I know. It's like, dude. So anyway, you'll get different, the stoichiometry and the molar masses are different, so you'll get different answers, you know. Any questions about that one? Okay. I agree. And then the next one looks like this. You know, I'm notorious for, I like to write the masses underneath what I know. And here I color-coded them because there's two different questions. Okay, so. Yep. We could do that. And then this one, if you read it, you'll see that, again, we have the mass of aluminum, and they're wanting to know the mass of H2SO4 and the mass of H2. So,
So what we just
that's it. Yep, what we just did. Yep, that'd be good. Okay. So, a couple of things that we talked about yesterday. We said that when you guys did, anytime you do a grams to grams, like stoichiometric calculation, and what you're after is a product, that's like the brownies, that's like the yield. Okay, that's the yield. Okay, so theoretical yields are is the calculation part to think how much you should get back. Now the term theory kind of implies it's like, well, and I don't like this when we talk about the scientific method, and a theory is a big, hairy deal. But when people say it's just a theory, it means sometimes they say, well, it's just, they don't really know. So theoretical yields are, you really don't know for sure that's what you get back. So I've got a little bit of discussion here. Now this topic oftentimes shows up on my 4th unit exam when I'm looking for stuff to test you over. Because I think it's important, like for instance, yesterday, when you were coming up with your actual CO2 yields, usually they were, was it lower or higher?
I know ours was off by quite a bit, but I don't know if it was higher.
I think they were biased lower.
Yeah, our actual stuff that was produced was lower than the theoretical
Yeah.
one.
And actually, this list I'm going to go through is all reasons why it would be lower, why your actual is lower than theoretical. So this might make you feel better. Okay? So the first one I want to kind of run past you is reaction kinetics. That's kind of how fast your reaction occurs. The other one is chemical equilibrium. I love chemical equilibria. It's basically, we're all about saying a chemical reaction proceeds, like as a sentence proceeds from left to right. So we do this R for reactants, reaction arrow goes to form product. Okay, but there's a lot of chemical processes out there that actually, they go that way from left to right, and they also go from right back to left again. So they are actually shown with a two-way arrow. That's a chemical equilibrium. That's so cool. So that's one reason why your yields are low. Another one, and actually we ran into this with when you guys took your magnesium and you burn it, Okay, a side reaction was where your magnesium didn't combine with oxygen, but it combined with nitrogen. So that was an unwanted side reaction. You're like, well, I can't help that. Okay. And then the other one is physical losses. Now, physical losses shouldn't be confused with the oops or crap losses, you know, where you just like kind of spill it. Okay, physical losses are something that are kind of inherent in the SOP for your procedure. Gross error is the oops. Yes. Okay, so I'm going to kind of break these down a little bit. And reaction kinetics, I said, is like how fast. Kinetics is how fast the reaction occurs. We think of reactions as kind of like the light, turning on the light switch and we automatically get light. Well, actually, that light takes a certain amount of time to get to our eyes, but it's so fast that we can't tell it. But chemical reactions oftentimes take a certain amount of time. So I have an example here. They're actually the red, down along the x-axis, think of it as time. Okay, so time is flowing on. And along the y-axis, we have concentration. The red is the reactant going away, going away, going away, going away. Okay, the green is the product forming, 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 forming. So the point here is that it takes a certain amount of time for all of your reactants to form products. So this is our reactant, and this is our product. So products are building, reactants are getting less. So the point here at the caption says, what if we were to go ahead and pull the product at 7 seconds? Let's see, 7 seconds, so that's 8, so 7's right about here. Okay, 7 seconds. Okay, about 7 seconds, actually, that kind of intersects with, we about got half and half. We got about half of our reactants have been converted to products, and half of our products have been formed from reactants. So the point is there, you would get like 50% yield, right? Because the reaction kinetics. The equilibrium I mentioned, kind of the back and forth. And you might imagine the thing here is if you're trying to grab the product and say, oh, that's my yield. Well, dang it, the product's going back to form reactants again. So you're never going to get 100% yield there. Okay, you just won't. So an example of a chemical equilibrium is where we have molecular H2 and I2. These are our reactants going to form the product here. Okay, so again, if we think of kind of the x-axis as being time, if we start out with only the reactants and no product, okay, over time our product will increase and our reactants will decrease. But notice that at some point, and I don't know where that would be, somewhere in here-ish, okay, basically it kind of flat lines. What the flat lines mean is basically it's at chemical equilibrium. It's still dynamic. We still have the H2 and I2 going to form 2HI, and the 2HI breaking down to form the H2I2, but the rates are the same. So there you go. Oops, sorry. This one was, oh, goodness gracious. Okay, this one was like the N2 combining with your magnesium, okay? So some of the product would be magnesium nitride instead of magnesium oxide. Physical losses, again, it's just kind of inherent. If your chemical or if your experimental write-up requires you to do some transferring from one beaker to another, okay, you can't help it. You're going to actually lose some residue on the side. Sometimes purification steps are notorious for losing product. So, goodness gracious, this thing is just not wanting to work. Pharmaceuticals are an area, obviously, where they don't want any contaminant to be transferred to the people consuming their pharmaceuticals. The other thing is they don't want any stray chemicals. So they actually lose a little bit of their product at the expense of purifying it. So when you guys go mass of a reactant to mass of a product, your theoretical yields, that's in a perfect situation. If all of your reactant reacted, okay, and if there were no side reactions, okay, and if you were able to isolate all of your product. Okay, so odds of getting 100% yield are not real good. But those examples I said before of not getting 100% yield are all biased low. Okay? So here's the oops error. Okay? And again, on your unit exam, you're going to see me probably test you over these things. So if you're in the lab and you do something that was avoidable, that's a gross error. Now, no offense, we've all made them. Okay? They include things like, oops, sorry. Yeah. They include things like if you spill some material, that was avoidable. If you misread your balance, or if you misread like a volumetric flask or a graduated cylinder, if you misread those. If you screw up in your calculations, that's a gross error, and that can maybe propagate through, okay, to some problems. Not following instructions, for whatever reason. Again, I'm not trying to pick on anybody, but these are all gross errors due solely to the ineptness of the investigator. That sounds mean. All I gotta say is nobody's blowing up the lab this semester, so. So, this one then, this actually, if it goes to the next slide, was something I mentioned we could have done with your calculations yesterday. I chose not to. But remember at the end when I came through and looked at your calculations, I looked at what you got back, so number 10, and I looked at your CO2 stoichiometric calculation. Okay, so that was your theoretical yield versus your actual. We could have done this with your numbers. If we wanted to come up with percent yield, we would have just taken your actual divided by your theoretical. So again, your theoretical is from a stoichiometric calculation, your actual is what you really got back. So usually it'll be less than 100%. So if we look at an example, we go back to this example. Now we're not going to do a stoichiometric calculation with this because we already have. Remember on Wednesday we did the 1.25 grams of CL2, 1.25 grams of CL2, question mark grams of PCl3, and we came up with 1.61 grams. Okay, so that was a theoretical yield since it's a product and we did the stoichiometric calculation. So let's say that instead of getting 1.61, what if you only got 1.08? Like, oh crap. Well, you know what? That might be about as good as you can do. Okay? So you were low, and then so to knock out the percent yield, all we got to do is take that actual 1.08 grams and divide it by the theoretical 1.61 grams. And we have 3 significant figures there, and then take it times 100% to get in parts per 100. We have 3 significant figures in those masses, so that gives us 67.1% recovery. So, again, that might just be pretty darn good. I kind of imagine these percent yields as if you're in the factory setting, they're all over the place, especially if you're doing wet chemistry. Like, what is our yield? And are we doing the best that we can? Are we squeezing everything we can out of those chemicals? So this assignment will also be due, and I'm not sure I have that one to show you. Now my time matches up with that time, so 8:59:60. Might be down here. Yeah, I think it is. No, that's not it. Here it is. Okay. Sending project. Match. Bless you. Bless you. It doesn't want to match. But I'm looking at it right here in my iPad, and I think you should be fine. What they both do is they give you the theoretical yields and the actual yields. So it's just a quick division problem. Okay, on to the last subject. There are no homework problems related to this concept. Okay, on to the last concept. So remember the HCl calculation you guys did? and I said, you guys did the 2 boxes. The first box was stoichiometric calculation, and the second box was how much HCl did you actually have. And kind of in closing, I went around, I said, did you notice you had a lot more HCl than your stoichiometric calculation said you needed?
You called it excess.
Excess, that's right. HCl was excess, exactly. And so there were only 2 reactants in the from the HCl. The other one was the NaHCO3. That actually was in what we call limited supply. You're going to use it all up, okay? So I have some examples here. Like, let's just say you went to your cupboard. Let's go back to the brownies. This is the same recipe we looked at before. And let's just say you have 8 eggs. You have 2 cups of sugar. You have 2 cups of brown sugar. You have 16 ounces of butter. You have 2.5 cups of cocoa. You have 1 teaspoon of vanilla. Oh, sorry. You have 2 teaspoons, because then you're going to make a half batch. You have 2 teaspoons of vanilla, 1 cup of flour, and you have 1 cup of salt. Sorry, not 1 cup of salt. One teaspoon of salt. Oh my gosh. My point here is that do you see that we could make 2 batches, but we can't make 2 batches. Why? Because of the vanilla. And if you're like me, you could go with a little less vanilla, so that'd probably be okay. But the vanilla was limited. It basically is your short chain. You can only make 1 batch. So kind of a similar thing here. Now we've got, if you're going to be chintzy with the ham, only give 1 sandwich, or each sandwich has 1 piece of ham. This is how you make ham sandwiches. So what if you go to your cupboard and you have 20 slices of bread and 7 slices of ham, and you want to make as many sandwiches as possible? How many sandwiches can you make, and why? You could only make 7, right. You can only make 7. Why?
Takes 14 slices of bread.
That'd be 14
for
slices of
7
bread.
slices.
Yep. Takes 14 slices of bread. You'd have 6 slices of bread left over, but you'd use all of your ham. So which one's limited?
The ham.
The ham is limited. Exactly.
Unless you're really chintzy.
Half a ham. This one actually switches gears, and we could do like a little bit of math kind of behind the scenes. But in this class, I don't really emphasize the whole identifying the limited supply reactant. That's actually for general chemistry. But if we did this, we actually would see which one was in limited supply. Okay, so just to kind of summarize, the one that's in limited supply then is the one you're going to run out of first. And if it's in limited supply, then it drives the reaction. So it says how much product's going to be produced. It says how many other reactants are going to be consumed. Okay. So, but with all of that said, we've been doing, in this part we did stoichiometric calculations, okay? And I didn't make you do on the front end identify which one you're going to run out first. That's like a separate problem. So this is actually called ordinary stoichiometry problems, okay? The other one are called limited supply stoichiometric calculations. You have to do a front end, which one you're going to run out first, and then kind of do your ordinary stoichiometric.
Is this going to be on the test?
The concept of limited supply reactant might. So yeah. Okay, that's all I had.
Yay!
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 Oh,
Bring us back to me, leave it on my desk when you're done with it.
lottery. Thank you. Okay.
We're gonna get rich and abandon everybody.
Well, not this semester. Well, I'll do out my semester, but
I'm abandoned all.
yes, I do.
I'm one of those people who comes to the smack off.
Are the heaters the?
Oh, I don't know. I'm still in news blackout, so
Me too. News
News
blackout.
blackout.
I don't know who won the election.
Yeah, I don't either.
But somebody told me like they found water like under the surface of Pluto, and that's the sort of news I should be
Yeah, that's the
tuning
stuff
in
that I
on.
look
you
I was
know?
watching Cosmos last night.
Oh,
Have you watched any of it?
Yes.
About
All of it.
Oh, you
Carl
have?
Sagan's.
the old one and the new one?
Yeah. Carl Sagan's and.
What'd you think of it, Ben?
I thought it was pretty cool. It was about, the episode I watched was lead. The toxin in the air from the lead or whatever. The guy who founded how old the earth was. What was his name?
He's from Iowa. He was a chemist from Iowa.
Oh, dang.
Yeah, he was.
I don't remember that
He was the
episode.
one that said everyone's getting lead
Lead
poisoning
poisoning from
and
the
the
gas.
oil
Oh,
companies
yeah.
were like,
Yeah, so he
No,
fought
they're not.
them. He
He's
fought
like-
those
Yeah,
corporations for like 20
that was
plus years
neat.
in order to
I
get
forgot about
yeah,
that
to get
episode.
it banned out of gasoline.
Awesome. So,
I'm just sitting here, I was gonna tell you, if you don't have money with you, just put it in that top drawer so that it don't disappear.
okay, I do have money, and so I'm gonna put it on your desk then, in your,
Well, unless you want me to wait right here, right now,
okay, well, I'm headed back to my office.
I'm going the other way, so
Okay,
I'll just wait here.
okay, sounds
It's
good.
up to you. I just didn't wanna interrupt your class. But
Well, I
heard
appreciate you
say- I
finding
heard
me.
you say it was over, so
Yeah. And they all went, hey!
I heard that.